Hello, thank you for tuning in. My name is Jeff Taylor. I'm a PhD candidate at Utah State University, and today I'm going to be talking about a numerical method that we developed for rapid aerostructural design and optimization. And this is really part of a larger body of work that I've been part of at Utah State University to develop analytical and low-order methods for really understanding the coupling, the aerodynamic and structural coupling involved in aerostructural optimization. So I hope I can make this interesting and I hope it's enjoyable. And here we go. So I'll start out today by uh, going over a little bit of this larger body of work that I've talked about. I'm going to give a brief overview of the analytical foundation of the work and then describe how we were able to modify some of the analytical models to predict the wing structure weight and induced drag for a little bit more realistic aircraft concepts. Then I'm going to be showing the results of a case study that we performed using these methods on the NASA Icona airframe. And then I'm going to talk about how these methods can be used for design space visualization and exploration and for understanding some of the sensitivities of the optimum solution to certain design parameters. And then along the way, we'll pick up a few additional insights that I'll highlight. So I want to start off a little bit by giving some context as to why we are dealing with low fidelity methods. And really the main reason is that low fidelity methods provide insight that's not easily obtained using high fidelity methods. And just as an illustration of this, I've shown here 6 examples of insights that we've gained from early analytic aerodynamic models and these are kind of foundational to our current understanding of aerodynamics, these among others. So we have the shape of the boundary layer here in the top left, the idea that the lift slope of a thin airfoil is nearly 2 pi, or that the quarter chord is kind of the theoretical location of the aerodynamic center for an airfoil. And then these 3 bottom pictures are about the induced drag. So the concept of induced drag was first found using an analytic model based on lifting line theory. And from it, we learned that the induced drag coefficient can be decreased by increasing the aspect ratio of a wing, and also that the optimum lift distribution on a wing with fixed wing weight and wingspan is the elliptic lift distribution. And these are kind of foundational things that come up all the time when we're talking about aerodynamics. And the same principle holds true when we're talking about aerostructural design and optimization. And another reason that we want to use high fidelity or low fidelity methods is because they're useful for understanding and visualizing the design space. So high fidelity methods, like as is represented by this picture here on the left bottom, are very, very good for identifying an optimum solution. So here on the right, we have a representation of a simplified design space for drag on a wing as a function of 2 variables, x and y. These are just generic variables. The minimum here is this black dot. And so the high fidelity methods are very good at identifying that point and also the area immediately around it. And they're especially good if we start off with a really good initial guess. But and because of this, they're very good at later design phases when we have our design already somewhat nailed down and we can just really refine on it and find this optimum. Now, low fidelity methods, on the other hand, are generally very fast, and so they can be used to visualize and predict the whole design space, a much larger window of it anyway. And so we can rapidly iterate on design concepts, and we can kind of understand the different trade-offs between different design parameters and different variables. That's extremely valuable during conceptual design and optimization. So Prandtl seems to be the first to have really approached aerostructural design from an analytic point of view, and he did this in 1933. Since then, since the early days, really aerostructural optimization has trended more and more towards high fidelity, and there's really not a lot of modern studies that approach it from an analytic point of view. But the way that Prandtl approached it was he noted that the induced drag is a function of the weight, the wingspan, and the lift distribution. And using classical lifting line theory, the lift distribution can be described using these Fourier coefficients, this B sub n. So throughout this presentation, I'll be talking about different B sub n coefficients, and these are just a representation of the lift distribution. So if we want to minimize this equation, this induced drag, and we have a fixed weight and a fixed wingspan, the best way to do that is by just setting all of the Fourier coefficients to 0. Well, this gives the well-known elliptic lift distribution. If we allow the weight and the wingspan to vary, however, then we can see that we would want to minimize weight and maximize the wingspan. But we can't do this arbitrarily because the weight and the wingspan and the lift distribution are all coupled together. So we have to consider all three when we're looking to minimize induced drag with structural constraints. So Prandtl took advantage of these trade-offs between weight, wingspan, and lift distribution and identified a bell-shaped lift distribution that minimizes induced drag on a rectangular wing. And it allows a 22.5% increase in the wingspan for the same total weight. And that's what allows it to achieve a reduction in induced drag. And the reduction that's possible is 11.1%. Notice that Prandtl's 1933 lift distribution differs from the elliptic lift distribution only in the third Fourier coefficient, whereas the elliptic lift distribution has all the Fourier coefficients at 0. Prandtl's 1933 lift distribution has B3 equals -1/3. Now Prandtl made some assumptions in his study that are not really representative of most aircraft. In particular, he assumed that the moments are only due to the lift distribution, meaning that there's no load alleviation from the weight. He also assumed that the wing structure weight is related to the bending moments by a somewhat arbitrary proportionality coefficient that's invariant across the span. And really what this boils down to is that Prandtl's approach really is only applicable to rectangular wings. Recently, however, Phillips and others, including myself, have taken another look at this problem and rehashed some of Prandtl's original work and relaxed some of his main assumptions. In particular, we allowed the moments to be produced by the lift and the weight distribution, and we related this arbitrary proportionality coefficient to the spar structural and material properties. And we identified several different lift distributions that minimize induced drag depending on the design constraints. And we looked at several different sets of design constraints. Here I have shown optimum lift distributions for stress and deflection limited designs of wings with fixed wing loading or fixed fall speed. And you can see that each is different from the other. However, all are part of the same family of lift distributions that only differ in the third Fourier coefficient. It's also interesting to note that the optimum designs that result from this optimization with these constraints result in a wing structure weight that is 1/2 the weight of all other components in the wing for the stress limited design, and a wing structure weight that's 1/4 the weight of all the other components in the wing for the deflection limited design. Now, there are limitations to this approach as well. In particular, although we express things in a more general form, in order to obtain analytic results, we had to assume that the section weight distribution followed this ideal shape. That's really not representative of typical aircraft weight distribution. We also had to assume that the chord distribution followed some given function. So originally we started with rectangular wings, and then we extended the work to elliptically tapered wings and linearly tapered wings. And really what we found is that the optimum lift distribution is not sensitive to the degree of taper that's used. So now what we're trying to do today, and what I'm presenting today, is work that we did to further extend Phillips's work to move away from these ideal chord distributions and weight distributions toward more representative chord and weight distributions of real aircraft that we see out flying today. So we may have double taper, we may have discontinuous chord distributions, or we may have a wing that carries fuel or engines or other external stores on the wing that contribute to the weight distribution. And so we want to be able to accommodate all those different things. But in order to do that, we have to, I guess, supplement our analytic methods with some numerical methods. So the first challenge, and really the main challenge that we have, is how do we relate the wing structure weight and find the wing structure weight as a function of the wingspan and the lift distribution, since all three variables are coupled. And so for the stress limited design of a wing, we can express the wing structure weight using this equation. Now, the middle term here is very similar to what we saw for Prandtl's assumptions, that the wing structure weight is related to the bending moments by a proportionality coefficient. But here, whereas Prandtl assumed that the proportionality coefficient was invariant across the span, we recognize that it may vary across the span. And that really depends on the design of the spar and its material, as we can see on the right. So on the right, we have the very same expression, but we've now used the definition for the proportionality coefficient as a function of the spar material and structural properties. So what I really want to point out here is that in order to predict the wing structure weight, we have to integrate the chord distribution. And this can be done analytically for certain chord distributions, but if we're talking about arbitrary chord distributions, we may have some that we have to integrate numerically. So we need to use numerical integration to accommodate these arbitrary chord distributions. We also have to do some special treatments for the bending moment. And the reason for this is because the bending moment is actually a function of the lift and the weight distribution. But in turn, the weight distribution is a function of the bending moments. So we have this coupling that we have to resolve, and that can be most easily done using an iterative method. So shown here on the right is a schematic of the iterative method that we used to predict the wing structure weight. And it starts by inputting known parameters. So these are wing structural parameters as well as the lift distribution and the wingspan. And then from there we calculate the weight properties of the wing. And then the wing structure must be sized to accommodate and support the bending moments caused during a high load maneuver as well as a negative load maneuver such as a hard landing. And so we have to examine the bending moments from both those cases and take the bending moment that has the higher magnitude at each section for our wing structure weight sizing. And then we relate that bending moment to the wing structure weight using the proportionality coefficient, as we talked about before, and for a wing with arbitrary planform that requires numerical integration. And then when we look at the wing structure weight, we have to consider both the stress and deflection limited designs, because the way that the wing structure weight relates to the bending moments depends on whether we're looking at stress limits or deflection limits. And so we calculate both, and then we take again the max magnitude wing structure weight at each section and integrate it to obtain our final wing structure weight for that iteration. And then we continue to iterate until the wing structure weight has converged to within some specified tolerance. Once we have an estimate for the wing structure weight, we can plug that back into our equation for the induced drag, and we can obtain an estimate for the induced drag for a given wingspan and lift distribution that accounts for how those affect the wing structure weight. And what this really facilitates now is then the minimization of induced drag on a wing. And this is done really very in a straightforward way. We just put our method for estimating the induced drag with the wing structure weight taken into account. We use that as an objective function inside an optimization framework. And it's really not there's no fancy things that are going on here. But I want to point out that for this study, we tried to enforce constraints that were typical of, the representative of typical aircraft. So we fixed the wing loading, and the reason for that is so that we have an optimized design and a baseline design that has similar performance characteristics, since the performance is related to the wing loading. And we also fixed the payload weight, since most aircraft are designed to carry a specified payload over some given flight profile. And we allowed the wing structure weight to vary as it needed to support the bending moments for that given payload weight. We also enforced spar width and height constraints so that the spar is ensured to fit inside the airfoil. We don't have spars sticking out of the airfoil skin. and we also enforced an all positive lift distribution. So we applied all these things we applied this method to two example configurations of the NASA Icana airframe. Now the NASA Icana airframe is a modified Predator B airframe, and most of the geometric and performance characteristics of Icana can be obtained from publicly available data, and the remaining can be inferred from publicly available data. So the Icana has a tapered wing with an aspect ratio of just over 16 and a taper ratio of just over 4. It has a thick airfoil at the root and tip. The wingspan is 66 feet. From available data, we can infer, assuming that the fuel is all carried in tanks in the wing and that the wing tanks scale according to the local chord, we can infer that the Icana would carry fuel in tanks that extend to about 80% of the semispan. And so I guess additionally, the Icana sometimes carries a instrumentation pod that weighs 500 pounds at a point that's 25% of the semispan. Now we looked at two configurations, one that has the instrumentation pod and one that doesn't. And the weight distribution for the pod configuration is shown here on the right. Now the results of the optimization are shown here for the pod configuration, the no pod configuration above and the pod configuration below. So the wingspan for both increased between 15 and 20%, and this resulted in a reduction in induced drag of between 8 and 9%. It's interesting to note, however, that the optimum wing structure weight, or the wing structure weight for the optimum design, is very close to the quarter of the weight of all other components that was predicted analytically by Phillips for a rectangular wing. It's also interesting to note that the lift distribution is very similar to the lift distribution for the deflection limited design of a rectangular wing, which is its curve D shown here, just the dotted lines, where the optimum lift distributions for the no pod and pod configurations of Icana are shown in black. So you can see that these lift distributions are very close to one another. This suggests that the analytic solutions are actually really a pretty good approximation. It's kind of remarkable considering how different Icana's weight distribution and planform are from those assumed by Phillips. So to take a look at the design space around this optimum solution, we were able to do this with our methods. We just ran the induced drag predictor using the wing structure weight iterative solver, and we ran it at about 100,000 different points in the design space and obtained this visualization. We were able to do this in a matter of seconds on a desktop computer, whereas a high fidelity method would take days really to produce a plot like this. So you can see the baseline design is in the top left hand of this plot, and the optimum design is kind of in the top middle. It's interesting to note on this plot that what we see here is the variation in induced drag with changes in wingspan and lift distribution, which is parameterized by B3. But it's interesting to note that the weight changes throughout this design space, and it changes in such a way that the bottom left corner represent low weight designs. But that corner is also where the highest drag occurs in the design space. So really the low weight designs in that region correspond to high drag. So this kind of raises an interesting point, and it kind of illustrates the trade-off and the competing design objectives between minimizing weight and minimizing drag in some cases. We can see that if we start at the baseline design and our goal is to minimize drag, then we would immediately want to increase the wingspan to approach our optimum design. However, that incurs a penalty in weight. But it is better for us to increase the weight and take that penalty by increasing the wingspan than to try to minimize the drag by changing the lift distribution and decreasing the weight around the baseline design. At other points in the design space, however, like in the top middle, we can decrease weight and we can decrease weight and induce drag by changing the lift distribution. And so those design objectives are no longer competing in that area. So this design space illustration shows that at different points, depending on where your design falls in the design space, it may be better to increase the weight or decrease the weight, or increase the wingspan or decrease the wingspan, or change the lift distribution. And it's important to know where we fall in the design space to understand which of these variables we should change. We can also, using these methods, figure out which of our parameters affect the optimum solution. So what we showed in the previous slide is the induced drag is a function of 2 design variables. However, there are several parameters of variables that could be changed to change that optimum solution. So we looked at how changes in pod location, root weight, proportionality coefficient, wing loading, and taper ratio all affect the optimum solution. And so we can see from these 2 plots, this is pod location and root weight, that if we change the way the weight is distributed in the wing, it really has most of its effect on the lift distribution, but really doesn't affect the optimum drag, optimum wingspan, wing structure weight, or corresponding induced drag very much. If we change the proportionality coefficient or the wing loading, we can see that we don't affect the wing structure weight at all, and we don't affect the optimum lift distribution at all, but we do get large changes in induced drag and wingspan. And that's because both of these parameters have to do with the way that the structure carries the lift distribution and how efficiently they can do it. And finally, we see that if we vary taper ratio, we don't change our optimum design very much at all. And this really supports the result found by Phillips and his group that the optimum lift distribution really is insensitive to the taper ratio. And we also see that the optimum design really is also relatively insensitive to the taper ratio. So just to conclude, the wing structure weight can be related to the wingspan and the lift distribution using analytical methods. But in order to accommodate arbitrary weight distributions and arbitrary chord distributions, we have to use some numerical methods. We have to use iteration to account for the coupling between the bending moments and the wing structure weight, and we have to use numerical integration to account for arbitrary chord distributions. We showed through our case study that depending on our designs, our optimum solution can produce up to 9% less induced drag than the baseline design. But really the power of this method comes in the fact that it's fast, and by using it we can visualize a design space and explore the design space very rapidly to gain important insights into the importance of different design parameters and variables at different points in the design space. And then we also found that the optimum lift distribution is most sensitive to the weight distribution, and that really a lot of the analytic solutions that we've derived for rectangular wings can apply also to other wing configurations and more realistic wing configurations. And so that's pretty remarkable. And with that, I'll conclude. Thank you for tuning in.